Today, I'm very excited to introduce the work puzzle, efficiently aligning large language models through lightweight context switch. This work is conducted by Kinman Lee and other colleagues in the Pacman group from Tsinghua University. In recent years, large language models have emerged as a powerful technology around the world. During the process of training LLM, aligning large language models is a key technique. This technique ensures the outputs of LLM adhere to social ethical standards and improve accuracy. Since aligning is crucial for security of LLM, it has been widely applied in popular models such as ChatGPT and Llama. Among the alignment methods, reinforcement learning from human feedback, also known as RLHF in short, stands out as the primary method for alignment. Now, we are going to have a brief introduction to RLHF. Let's start from reinforcement learning and human feedback separately. Here we show an example of RLHF, of reinforcement learning. In this example, an agent plays the game. At first, the game presents the current state to the agent. Then the agent decides on an action to perform based on the given state. Once the action is executed, the game provides feedback in the form of a reward. And according to this reward, the agent improves its action to maximize future rewards. The example in the right shows the workflow of human feedback. When we input a prompt into the LLM, for example, Kobe Bryant is a who or what. This is an incomplete sentence. LLM may generate responses such as basketball player or football player. The role of human feedback here is to evaluate the responses generated by LLM and score them based on their accuracy and relevance. By combining reinforcement learning and human feedback, we can have the RLHF algorithm. RLHF aims to align LLM more closely with human experience by reinforcement learning. As shown in this slide, we can use human feedback on the right part to replace the steps on the left part. First, the agent is replaced by the LLM, and the state corresponds to the prompt given to the LLM, and the action in the answer generated by the LLM based on the prompt. And the game is substituted by humans who evaluate the quality of the responses from LLM. And finally, the reward is the score from humans. And this is the whole picture of RLHF. However, it's important to see this way is impractical to evaluate every answer by human due to the extremely high cost. To solve this problem, we can employ another LLM to simulate human evaluation. And at last, as we can see, this scenario involves two models. After knowing the high-level idea of RLHF, let's focus on the most widely used RLHF algorithm, proximal policy optimization, and PPO in short. The workflow of PPO is more complex. Initially, a given prompt is processed by the actor, which is an LLM, and it generates an answer. The answer is then evaluated by another LLM called reward. Additionally, two new models, the ref and the critic model, are introduced. Their outputs contribute to what is called experience. Next, the experience is utilized by both the actor and the critic to update their parameters. Therefore, we have 4 distinct LLMs and different workloads here in this process. To better schedule the workflow, we can divide the entire workflow in different stages according to data dependency. For example, these 3 models, the reward, ref, and the critic models, are without dependency, so we can put them into a single stage. And the 2 actor models in the slide have dependency, so they are in different stages. For this workflow, we have 3 stages in total. However, while PPO is an efficient and important method, it imposes unique challenges on systems. Let's compare the workload of classic tasks with that of aligning. In existing systems for inference and fine-tuning, a single model handles a consistent workload throughout the entire process. However, aligning requires multiple models with heterogeneous workload. Here, we can regard the model as a context, and the workload shown in the figure as the stage for better presentation. And therefore, the alignment involves frequent context switching, and this context switching adds complexity to the underlying system. By analyzing the workflow of RLHF, we find that the key challenge of RLHF is to efficiently switch heterogeneous contexts. Such frequent context switching results in significant overhead, including model reloading, parameter updates, and data transfer, and so on. We focus on two specific challenges, the intra-stage context switch and the inter-stage context switch. The first challenge is intra-stage context switching. Here, we consider the 3D parallelism that are data, tensor, and pipeline parallelism are utilized in our system. And the problem lies here is how to leverage the dependency-free nature of the context in a single stage. While existing systems already support many placement and execution plans, we observe that in the optimal plan for a stage, there is still much idle time. The reason is that model execution plans are sequential in the existing systems. If we can take use of the idle time, more efficient plans are possible. And to improve the efficiency within a single stage, it's important to explore the overlaps between independent contexts. Therefore, we need to explore a larger space of placement and execution plans. The second challenge is interstage context switching. First, we notice that different workload characteristics have various optimal parallel plans. As we can see in this figure, the generation workload is better on a parallel plan with a pipeline parallelism of 4 and the tensor parallelism of 2. However, the training workload is better with a plan which is pure pipeline parallelism. Moreover, we notice that the parameter transformation between different plans can also have larger overhead. In the evaluation of DeepSpeed-Chat, it accounts for 12% of the execution time. In the figure on the right, it shows the transformation overhead between different plans. The overhead depends on both original plan and the target plan. So it's necessary to consider these characteristics in order to reduce the transformation overhead. Therefore, for an efficient system for LLM alignment, regarding the intra-stage context switch, it should explore an enlarged search space of the model placement and execution plan, and it should select a plan from this space to reduce idle time as much as possible. And to deal with the interstage context switching, the system should consider workload to choose an execution plan to minimize the transformation overhead. To address this problem, we implement an RLHF framework puzzle. For the intra-stage context switch, we propose an enlarged space for placement and execution plan, which support nearly bubble-free switching. And for the interstage context switch, we propose a lightweight workload-aware switching method, which handles different workload characteristics in various parallel plans to improve the performance. Now, let's look into the details of how the proposed techniques make puzzle an efficient LLM alignment system. First, we analyze the overhead and opportunities in intra-stage context switch. We focus on overhead from pipeline parallelism, which is often referred to as bubbles. As shown in the slide, two model pipelines are executed sequentially. Since these models run independently of each other, we see a lot of idle time between the two models. To address this issue, we expand the execution plan space by exploring overlaps in different contexts that are independently with each other. In this scenario, we propose a time-sharing strategy to investigate the overlapping execution contexts. As shown in the slide, we can utilize the operations of the subsequent model to fill the gaps left by the previous model. This is feasible because there are no dependencies between them. By filling these gaps, we effectively optimize hardware utilizations without increasing memory consumption. Based on time-sharing switch, our system is able to consider both classic and new plans. Here, we show 3 existing plans, keeping isolated execution for each model context. Besides them, the proposed new time-sharing technique is able to improve the performance when 2 model contexts are executed sequentially within a stage. We can also apply different plans to a single stage in order to further optimize each context. Therefore, we can allocate better plans to each stage based on the given data graph. You can find more details in the paper about this part. And now, let's come to the second challenge. That's the interstage context switch. We use a lightweight workload-aware switching to deal with it. The core insight of our interstage switch lies in the finding that different workload characteristics require different parallel plans. Let's take an example of the switch from a training to a generation task. This switch requires adjustments to the execution plans. Thus, we can make use of the distinct demands of each stage, ensuring the optimal performance throughout the entire process. The training stage employs a parallel plan of 4-1, which means the pipeline and tensor parallelism configurations, and the execution time for this phase is time 1. Depending on the requirements, we may consider different transformations of the execution of the parallel plan. In the first plan, if we adjust the plan to 2-2, then the overhead from the parameter transfer is communication 1, and the execution time for this new configuration is time 2. Then the total time spent would be time 1 plus communication 1 plus time 2. And in the second scenario, we change the parallel plan to 1-4, and the total time would be time 1 plus communication 2 plus time 3. Our objective is to minimize the total execution time. So by analyzing these configurations, we can determine the most efficient parallel plan transformation. And for the details of the transformations, you can refer to our paper. And now I'm going to show the evaluation results of puzzle. We conduct the evaluation on 2 clusters with different types of GPU. They are NVIDIA A100 GPUs with the form factors of PCIe and SXM, respectively. To show the effectiveness of puzzle, we choose various LLM configurations and PPO hyperparameters with different actor and critic parameter sizes. We take DeepSpeed-Chat as a baseline in our evaluation. For the end-to-end speed-up, puzzle consistently outperforms the baselines across various PPO configurations and clusters. It's able to achieve up to 2.1 times speed-up. And on average, puzzle brings 1.8 times speed-up on the PCIe clusters and 1.5 times on the NVLink cluster. To show the effectiveness of the time-sharing plan, we compare the performance of using time-sharing plan within an intra-stage context switching. Our findings show that this plan can improve context switching performance within a stage, and it achieves a performance improvement of up to 1.12 times. And to show the effectiveness of the workload-aware transformations across different stages, we compare puzzle with and without this technique. This technique achieves an average speed-up of 1.22 times compared with the generation optimal plan, and achieves a speed-up of 1.34 times compared to the training optimal plan. In conclusion, puzzle is an efficient system for aligning LLMs. It regards model context as a first-class citizen. We propose a 2-stage technique to achieve efficient context switching. Firstly, it supports an enlarged space for placement and execution plan. This space includes time sharing to deal with the intra-stage context switching. And the second one is workload-aware switching to deal with the inter-stage context switching. Based on these techniques, puzzle achieves up to 2.1 times speed-up compared with existing systems. If you have any questions, feel free to reach out to the others via Slack or emails. Thank you for listening.